Hello, for today we're gonna tackle about the Brayton Cycle. Brayton Cycle was first uh, proposed by George Brayton for use in reciprocating oil burning engine that he developed around 1870. So the original Brayton engines used a piston compressor and piston expander, but more modern gas turbines engines and air breathing jet engines also follow the Brayton cycle, although the cycle is usually run as an open system, and indeed must be run as such if internal combustion is used. It is conventionally assumed for the purposes of thermodynamic analysis that the exhaust gases are used in the intake enabling analysis uh, as a closed system. So, as you can see in an open cycle turbine engine, as you can see in figure 929, and as you can see in the figure 930, it's an example of a closed cycle gas turbine engine. There is a difference between two. As you can see, it's a simple explanation. For this one, it's open cycle gas turbine. The process will not be like a chain, continue processing. Unlike this one, it is interconnected from 1 to 4. And unlike this one, it must be here in the column here, this hanging and not connected. So gas turbines usually operate in open cycle as shown in figure 19.1 in the past, maybe uh, past engines, but is indeed as this in this present more modern engines using a closed cycle. Brayton cycle is also useful in a closed cycle turbine engine. So there are four processes in a Brayton cycle, which the Brayton cycle represents the operation of a gas turbine engine. The cycle consists of these processes, which is very useful alongside a sketch of an engine, wherein we can easily understood the process or the ways uh, in determining uh, the problems involving Brayton cycles or the Joule cycle. So first, I want to talk isentropic compression. Uh, it is the adiabatic or aqueous static or reversible compression in the inlet or an compressor. 2 to 3 constant pressure heat addition, also useful, also called constant pressure fuel combustion, idealized as constant pressure heat addition, isentropic expansion in a turbine, or adiabatic quasi-static or reversible expansion in the turbine and exhaust nozzle, with which we take some work out of the air and use it to drive the compressor, and second, take the remaining work out and use it to accelerate fluid for jet propulsion, or to turn a generator for electrical power or regeneration for these 3 and 4 passes. And the last is 4 to 1 because it is a closed system which is interconnected. It will again end from 1 and start again from 1. So for 4 to 1, it states that constant pressure heat rejection and cool the air at a constant pressure back to its initial condition because it is a closed system. So again, the T's and PV diagrams of regular Brayton cycle are shown in figure 1981. So these T's and PV diagram are useful ways in determining or solving the problems, especially when difficult sketches or difficult height of a or sketch in every process of these four, uh, a little little challenging because some of this process may involve up to six. Involve not just like this four, it may turn to four, five, or six, something like that. But we are focusing here in maybe four to five maximum processes. So this one, the east and pivot diagrams of ideal Brayton cycle are shown in Figure 931. So you can see. Notice that all forces of the Brayton cycle are executed in steady flow devices. Those should be analyzed in the steady flow process. When the changes in kinetic potential are neglected, the energy back in the flow process can be expressed as a unit mass basis. So this is our basis for the unit mass. So this one, the Q, which is the heat added, and therefore the heat transfer to the form from the working fluid are this one. This is the formula, and this one for the out. I will tell you later what is the function or the meaning of this variable. So then the thermal efficiency of the ideal Brayton cycle under the cold air standard solutions becomes this 9 Brayton W net or out over QN, right, is equal to 1 minus the Q out over Qn is equal to 1 minus Cp T minus T4 minus T1 over CPT3 minus T2 is equal to 1, and this T times T over T4 over T1 minus 1, T2 times T3 over T2 minus 1. So this is the thermal efficiency of the Brayton cycle under the cold air standard solution becomes. Anyways, we can understand it more often or more harder when we try to solve this and use this kind of formula. Process 1, 2, and 3 and 4 are isentropic, which is P2 is equal to P3 and P4 is equal to P1. Thus T2 over T1 is equal to P2 over P1 is to K minus 1 over K, which is like this one, transposed to this one. So in Brayton is equal to this is the most or the common formula of the Brayton cycle. In Brayton is equal 1 minus 1 over the R to PR raised to K minus 1 over K. The idealized Brayton cycle where P is the pressure, so V is the volume, T is the temperature, is the entropy, and Q is the heat added or rejected by the system. So this is our ideal gas properties of air, which is useful because some Brayton, most often Brayton cycle uses air standard processes or the ideal gas properties of air. So kinda like this table because if for example there's a value of T, you can easily analyze the value of the pressure ratio and its volume ratio, and it's very constant values, and you will not be lost in solving or seeking for its values because it's given table for free. So kind of stretch our brains, kind of challenge problems. So first problem is a gas turbine power plant operating on a ideal Brayton cycle as a pressure ratio of 8. The gas temperature is 300 K at a compressor Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the air standard assumptions, determine first the gas temperature at the exits of the compressor and the turbine, B the back work ratio, and C the thermal efficiency. So first we can solve for the gas temperature at the exits of the compressor and the turbine. Just here we go solve the temperature. So first the temperature for the given standard key, which is used, as you can see, it's a basis in the H1 under the PRL. According to this table, you can see the value of standard is equal to 200.98. First, we have, for example, 300 for the temperature, and for the H is equal to 290. So just like that, you input kg over G as a sign given there. Let RW is equal to ratio of work for letter B. So to solve for the, as we also know that the PRL is 1.386 because it's also stated there 1.386. Yes, so you can input, so you can solve for the value of the PR2. So PR2 is equal to P2 over P1. PRL is equal to A times 1.386 is equal to 11.9. So PR2, so you can also convert this to temperature, just like the temperature converted to I mean the as equivalent value for or the ideal gas properties of air. So as the pressure of 11.9 may be equivalent to T2 is equal to 540 K according to the table in ideal gas properties of air, and also H2 is equal to 54425. As you can see this in the table here, it's only our basis in determining the temperature and its value for the pressure and the volume and ratio for pressure and volume ratio. So continue is first the process of 3 and 4. Why it's stated there why we use the process, because isentropic expansion into a turbine, because the turbine or process is expanding, and as you can see, different kinds of pressure, temperature is responsible and expansions of the process, which is called isentropic. So T2 minus 1300 Kelvin is about value of H3 is equal to 1395.87 kg per G. Also is equal to PR3 333.9. So first is the gas temperature of the existing compressor and the turbine. So this is this one. This is our first question for the PR3. So we have to solve for the we know that the PR1, PR2, PR3, and PR4. That is the most important, because the compressor it is very responsible in determining the any values in the compressor, because it must have the pressures done here in the compressor, so that we have to look for the pressure ratio. So the PR4 is equal to P4 over P3. This formula, as you can see, as we introduced in the upper part of this discussion, this is how you will need, or any other things you want to, any other formula you want to solve this kind of